All right, we're going to get started again. I'd really like to welcome our next presenters, Chet from Silicon Valley Power Authority, and also Aaron, one of our good partners at Petasense. So please, welcome to the stage. Thanks, guys.
Good morning, everyone. Thank you for coming out. My name is Chet Manchester. I'm the operations and maintenance manager for...
Is the mic up?
Oh, my mic?
Mic check.
All right.
Okay.
So my name is Chet Manchester. I'm the operations and maintenance manager.
Oops.
Pull out?
Yeah, it seems. Yeah. I'm on, right? Yeah. Okay.
All right. Well, let's jump to the end of the... Sorry.
Yeah, you should speak. I think you're on. No. The switch seems to be on. It's on.
So you want me to use this one? So, can everybody hear me now? How about now? No?
Dave, even this is not on. Level. Yeah.
Hello? Can you hear me now?
Yeah. Oh, okay.
Go with the handheld. All right, here we go. So, good morning, everyone. My name is Chet Manchester, and I'm the operations and maintenance manager for the city of Santa Clara here in Northern California. So, I'm a power plant professional. This isn't normally my gig, so I'm not quite as polished speaker as the previous one. So I'm still, in the trenches getting dirty. Been doing this for about 28 years, and so a little bit about Santa Clara. So Silicon Valley Power is a municipally owned electric utility in Santa Clara. We've been around for about 122 years. And we service the 19 square miles of Santa Clara. Fun facts about Santa Clara: we're 1% of all the power usage in California. We're also the cheapest power in California. We're a little bit upside down. We have about 54,000 electrical customers. 45,000 are residential, but that's only about 6% of our sales. 3% of our customer base is 90% of our power sales each year. We happen to be kind of the data center, server farm capital of the world. So if you're on your phone looking at Gmail or eBay, it's probably going through a server that's powered by it's one of our customers. So the Don Von Reesfeld power plant DVR went into commercial operation in 2005. It's a 2-on-1 power plant, 2G LM6000 PC gas turbines and a Mitsubishi steam turbine. We have about 150 different pumps, motors, fans in our balance of plant. So back in 2005, when the power plant was being built, we were looking at different data historians, and we looked at Pi and a few other competitors. We settled down. We settled with Pi, and a number of years ago we entered a enterprise agreement. As we were no longer using Pi just for generation. It went into our substations and onto our transmission lines and substations. So we're also using it as part of our smart meters. So we're going to be having 55,000 smart meters out there, and each one has about 30 Pi tags. So our tag count is really increasing. In the power plant, we're utilizing Pi to trend our parameters and look at our machine health and looking at efficiency of our heat exchangers and things like that. So one of the things that kind of drove us to wireless vibration monitoring and integration into Pi was back in December of a couple years ago, we had a catastrophic failure of a generator fan. And as a result of that, we were out for about 4 months. And we had a large loss of opportunity to make power during that period. Another example is, we have supplemental firing or duct firing. So if we lose a condensate pump, we have to derate the plant. A little bit about the catastrophic failure. The fan liberated from the shaft, bounced around like a pinball inside the enclosure, and became powderized, and all that aluminum got pulled into our generator. So needless to say, we had to pull the rotor and send it off to be cleaned and brought back, and it was just beyond words. And anybody that's in the power industry that's seen, catastrophic failure can kind of understand what we're going through. So prior to our wireless vibration, we had the traditional walk-around, route-based preventive maintenance. And for us, that, was what we did for since 2005. And, but, the guy shows up once a month, walks around, looks at the equipment that's running, and sometimes the equipment's running, sometimes it's not. He may or may not catch it on his route. So to prevent the ever having this catastrophic failure ever happen again, we knew we wanted something that was a little more continuous. So that's when we partnered up with Petasense and brought them in. We started off pretty small. We had about 24 motes initially. It's about the size of a D-size battery. Attaches right to the piece of equipment. And then every 3 hours it turns on and takes a sample and sends it off into the cloud. So kind of our basic infrastructure was the motes, and then we had a cellular gateway, and now we're moving to more of a Wi-Fi network infrastructure. We're pretty much covering all our stuff. Anything that would go down, it would cause us to derate or not be able to run. So our boiler feed pumps, condensate pumps, circ water aux, looking at fans on the cooling tower and the generators, and also looking at our gas compressors that we need to boost up the gas pressure. So one of the reasons we went with the wireless was really how fast we could roll it out. We didn't have to pull any wire. The cost of pulling copper in a power plant between the wire and the conduit and everything else is astronomical. This little JB weld and stick it on the motor, and it connects to the Wi-Fi and takes the data to the cloud, where we can monitor it on the web portal on a phone, anything that has a web browser. And then also we're going to start, we're bringing it into Pi, so we can monitor, look at this data along with all our existing instrumentation. The other things looked at were, beyond the cost of pulling wire, was added I/O counts, programming PLCs, the DCS, and things like that. So here you can kind of see, we'll kind of break that down. As far as rolling it out was, we had no cost or expenses due to pulling wire, doing conduit. There was no programming of the PLCs required. It's going to the cloud, so there's no, we don't have any problems with our IT department, and no system administration is needed. So it's a minimal burden on us. We're a really small electric utility. The entire utility is about 160 people. Generation is about 22 people. So, and we produce about a third of the power that Santa Clara consumes. So we're very small. So this slide we're talking about, we had this catastrophic failure of the generator fan. Like I said, it blew up. It was pretty crazy. But thanks to Petasense and the system, throughout the 2 years we've been partnered, we've been utilizing it. We've caught quite a number of different things that we probably wouldn't have kept before. Within 2 weeks of starting, we found a soft foot on a pump and got that corrected. And condensate pumps and water injection pumps and different stuff we found. So this was one of our motors, one of the generator fans. So back in August of 2017, we got an email notification that vibration had popped up above our setting. So we started looking at it over the next couple of days to see what was going on. We changed the sampling frequency from 3 hours down to 1 hour so we could monitor it. And then we greased the bearings a few times, which helped out. Then it came down for a few days, popped back up. At that point, we took the fan out of service. We checked the belt tension, re-greased the fan, and everything was great for about 2 weeks until it popped back up. And this is a little over a month, so maybe your vibration guy catches this, maybe he doesn't. So once it popped back up, we knew we had a serious bearing problem, and we took it out and replaced the bearings, replaced the belts, and if this extended any further, you would see that the vibration really leveled out and was back to normal. So we selected Pi kind of as our single source of where we're going to digest data. So we have trends on our control system, we have controls on the DCS, we have the web portal. So all 3 power plants that we operate come into here. Other systems in the power plant come in, and now the data from the Petasense cloud is coming in. So a lot of problems is we have a lot of machines that weren't instrumented properly or effectively when the power plant was built. Now we have the ability to add a lot of instrumentation wirelessly without the expense of wiring it in.
Yeah. Can you guys hear me? Yeah. So hi everyone. My name is Arun Santabanor, and I'm one of the co-founders of Petasense. So Thanks, Chet. We've been working with Silicon Valley Power for now about 2 years. I want to get into a little bit of the architecture. How did we make all of this happen, the integration with Pi? Because Chet was looking to make sure that all of this data can be put into Pi so that you can get a holistic system view and not just vibration alone, because vibration plus process gives them a more holistic view of all the machines and actually even identify process issues. From an architecture perspective, this data, this Petasense vibration mode uses Wi-Fi to send the data to the cloud, and Petasense Cloud can run on all kinds of cloud platforms. Today we run on Google Cloud, we've run on Microsoft Azure, Amazon, AWS, so we support multiple clouds. So the data goes to the cloud, and then we have a microservice. It's actually Petasense Pi service. It's a microservice-based architecture that runs there, that can integrate with essentially any Pi server. Okay, and then on the SVP data center, you can see the Petasense UFL client. That's a Python-based script program that runs, and you can schedule the task so it can go and get data from the Petasense Pi service, from that Petasense microservice. So it would be constantly getting data from the Petasense Pi service, and it uses web-based technology essentially to get all of that data, right? And then we had a few choices as to how we could integrate with Pi. We thought through, we actually worked very closely with the Pi team to discuss what the best architecture options are. We looked at Cloud Connect, we looked at a few other architecture options, and then we finally felt that the best option was using the UFL connector model. So today we run SVP, they have a UFL connector that runs in the REST server mode. So we take data from the Petasense Pi microservice and send the data to Pi data archive. So a lot of these machines were, so a lot of these points were, there are other points monitored. Let me put it this way. For example, a condensate pump. There were things like pressure, there were things like current that were already monitored. Now you can see vibration alongside, and I'll show you a few screenshots. So we would send the data to Pi data archive, and then so using Pi Vision, now you can see all this data. You can visualize all this data, right? The few points, you can be up and running. Frankly, this doesn't take too long. You have to go through the IT process of course, allowing us to run the client, but once you get that approval process run, it's literally a matter of hours before you can start seeing data into Pi. So once you solve those process issues, it doesn't take too long to get the data into Pi. Yeah. And I'll, after the presentation, happy to answer more questions about kind of the innards of the technology. So this is kind of how, one visualization that we built. There are several, we've built a lot of visualization on Pi Vision. Like you can see, this is a boiler feed pump. You can see a lot of parameters that SVP was collecting before. They were collecting things like discharge pressure, motor current. Now below, you can see vibration data, right? We just separated it out so you could see the process parameters on the top and the vibration data at the bottom. You could also set this up so that you could actually overlap this data, and we are doing some of that now. So see on the same chart, you can see pressure, and then you can see vibration, right? And the idea here is that you can catch a lot of system issues by seeing these things together. Yeah. So why do this, right? And we kind of alluded to this, but why integrate this kind of IoT data into Pi? Obviously SVP was a Pi Enterprise EA customer, so you can now put more tags and hence leverage your investment in Pi. So you can get all this. Typically, one of these can create almost 30 tags because there are a lot of features that can be migrated, into Pi. So now you can leverage all of those, and we see in an IoT world lots of sensors sending data to the cloud. They will go without going to the control system. They may not go to the cloud. They may go through a gateway. There are different architecture options available, but the point is they will go through a different route into Pi, not the traditional control systems way into Pi. So now by getting all these tags as an EA customer, you could leverage your investment in Pi. Now also there are a lot of personnel who are monitoring these Pis. They're looking at Pi systems and continuously monitoring all of that, and they traditionally did not have access to vibration data, or they did not have access to the health of these machines. They were looking at process parameters. So the same personnel can now look at asset health data. So essentially with this kind of an integration, as Chet mentioned, they want to make pi the single source of truth. So we want to make that integration seamless, right? So as a company, we believe that this is the customer's data. We need to make sure that we make it really easy and flexible to take this data and put it into any destination that they want, right? And oops, sorry. So getting into what were some of the use cases that we were looking to solve by getting this data together. It's one thing to predict, every time a pump fails, you can do that with vibration. But if you combine process data and vibration data, every day you can see if the pump is actually operating at its best efficiency point now, right? So, and you can take action immediately so that you're extending the life of your pumps, right? So that's one point. You can determine the health of your seals. You can identify system issues. So vibration is going up, but why is it exactly going up? Maybe there are some valves that are closed and things like that. By looking at all of this data together, you can identify those kinds of issues. They also SVP also wants to optimize the PM routes for several processes. We just mentioned one, the RO process. Do you really need to do PM at the schedule that you've been doing, right? There is a time-based schedule for a lot of these assets. Historically, that's what you've done because you've not collected data consistently. Now, by actually collecting all of this data every hour, every 3 hours, and trending against this, you'll have a lot more confidence to maybe prolong the life of your PM intervals. So that's really the other benefit. So I'll be here to answer some more questions on how we made the integration happen, but I'll turn it back to Chet to kind of what some of the key takeaways from this industrial IoT journey. I would just summarize with one thing. A lot of people talk about it, but Silicon Valley Power has actually gone ahead and done it, and they've been doing it for 2 years. They've reaped the benefits. Every now and then they get alerts. So they're a great customer to talk about how you can actually make this industrial IoT journey happen, right? So
yeah, well, we just don't want to repeat the mistakes of the past. We never want to experience a catastrophic event like that ever again. So just kind of to summarize some of the key takeaways, Pi is our single source. It's pulling in data from all our different assets, whether it's our DCS, our turbine control system, or from Petasense from the cloud. And we're using that data to help us plan our predictive maintenance, making sure that we're reliable, and online. And we're really using this IoT stuff to reduce our maintenance cost, eliminate unplanned forced outages, and and just the cost savings of not having to pull copper, do conduit, program PLCs, and stuff like that. So what's next for us? We're going to be looking to see where we can leverage a lot of this IoT technology. Petasense is coming out with a called the transmitter. So we're going to be installing that in places where we're under-instrumented, and we want to use it to help us get more analytics on machinery health and down the road. And hopefully with machine learning down the road, we won't need a mechanical engineer to be looking at our vibration data. The algorithm will start catching bearing faults at the moment that they start to show themselves. That's kind of it. So we're open for any questions that anybody might have.
Great job, guys. Awesome.
Oh, thank you.
Thanks. Being a small power producer does not mean it is not a super critical power producer. These guys are powering some of the most critical things that we all use every day. So I appreciate your time. I also think this is an excellent story, guys. Really the use of IoT. A lot of people are scared of it right now. Petasense is doing a fantastic job of letting you instrument things you don't normally have your instrumentation on. It's a cheaper way to instrument some critical assets. All right? And getting that data correlated with other data is you're going to need that if you move into advanced pattern recognition and machine learning, because that's where the value will come from. So we have any questions for Chet and Aaron?
Hi, thank you. That was great. My question is around the actual Petasense and the wireless. We obviously operate inside large power plants. I'm hydro, so these a lot of concrete. Did you find that you had to add more wireless systems, et cetera, to be able to harness that? We have a lot of dead zones in our plant. What does that look like?
So we had no wireless system like any other power plant. Everybody's kind of afraid of it. So we started off with one access point in our 24 moats, and as we expanded the system. So I think we have about, at DVR, we have about 150 of the
Moats.
175 moats,
Yeah.
and we have about 5 different Wi-Fi access points, and they're a few $100s to add, here and there.
Yeah, just overall what we've seen is as long as you have good cellular service, today it is big, you don't have cellular service, then you'll have to rely on satellite. I've actually gone to the middle of Colorado and tried to get satellite in a plant. So you have to rely on either cellular or satellite backhaul to get the data out. But cellular is inexpensive. Yeah, satellite is a little more expensive. If you have like some kind of a backhaul, the local Wi-Fi costs have really come down. Just getting a local Wi-Fi network, you can get access points and extenders for $100 and less each. So it's not that expensive to get the. But yeah, the backhaul is something for a very remote location. You have to use either cellular. Of course, they're bang in the middle of Santa Clara, great cellular. So.
But and it's pretty amazing. We were really surprised because, this is installed inside the fan,
Right.
right on the bearing, where it's surrounded by metal, and I was really surprised how fast we weren't going to have, a hard time getting the Wi-Fi signal. The bigger problem is our generator fans are in a confined space, so to change a $3 battery, we only have, a small window to make that happen. So.
In fact, he drove the development of our transmitter product, which is why we decided to get the battery module out, and so that there is a solution for that, for those kinds of assets. But even behind metal doors, like I think even the condensate, even the feed water pumps are all behind doors, right? Yeah. So.
Wi-Fi repeaters. It really works well, and like I said, they're actually cheap. So if you have a lot of dark spots within a big plant or your whole area doesn't have it, you can just put those repeaters in and get that information out.
Yeah, great use case, great presentation. My first question is the data resolution. You mentioned you collect every 3 hours, but at what resolution do you collect that vibration data? And the second one, you from your trend, you only showed one axis. Do you collect all 3 axis displacement?
Yeah.
So,
go ahead.
Yeah, so there are 2 models. They use model 1 mostly. Model 1, the resolution, the bandwidth is 1.6 kilohertz. We have another model that's a piezoelectric that goes up to 5.5 kilohertz. We just showed the overall, but it's a triaxial. It's a triaxial sensor. It collects vibration readings in all 3 axes, and it sends the full spectrum to the cloud.
Yeah. So we're looking at just a RMS value when we're comparing it to pi. If we want to see the waterfalls and everything, then we go into the portal, and it's all there. So.
Any other questions?
Hi, thanks for the presentation. I'm Alec Miller from Narrative Wave. Just curious as to the type of algorithms you're using. You mentioned machine learning. Are you using it to identify sort of the normal level, the average value, and then find if it crosses a threshold? Are you looking for trend lines, or are you doing a neural network type training as well? Thanks.
Cool. Yeah, I can take that. So right now, what we do is for each of these that are located on a spot, we generate a baseline of that specific, for that specific location where it is mounted, and the baseline is about a 30-40 dimensional baseline based on the type of asset. that we are monitoring. If you're monitoring a pump, maybe we will have a baseline not just of the overall RMSs, but maybe the vane pass frequency. So we select a lot of the features from the vibration to form a multidimensional baseline. So right now, what we have done in machine learning, I think I would say we are in like the first innings of the ball game. I don't think we are in the middle innings of the ball game. But the first part is to do some basic anomaly detection. So we have anomaly detection algorithms that can look at a baseline, a multidimensional baseline, and that can detect when it's deviating from the baseline to give a health score. And that's what they use, a health score between 1 and 10. 10 is perfect health. And then we also give a seed health score when we start monitoring. Maybe we start with an 8 because that's where the values are. And then we look at changes from that 8 from all these multi-dimensions, right? And that's what the machine learning is doing today. Eventually, we think it can do more in terms of preliminary diagnostics and things like that. But right now, what they are using is just a health score for each location.
Any more? We have some time, guys.
So you mentioned that you're doing multivariate anomaly detection just on the spectrum that you're getting from the sensor.
Mm-hmm.
How do you account for changes in operating conditions such
Right.
as speed and other things?
Absolutely. So that's really why the multi-parametric sense, the last part of the presentation he talked, the last slide, we are developing let me give you two answers. One, we do infer the speed from the harmonics today, but it's, I would say it works in 80% of the cases, so you could get the speed. But we also have a new product, please feel free to visit in our booth, a transmitter that can take speed input, that you can put a CT and get the speed and load and things like that, and you can have a baseline alongside that. Right now, that's not yet rolled out. It's a new product. Right now, it's vibration features, and the speed is determined from the harmonics. We detect the speed from the harmonics from the spectrum.
One quick question. How do you guys secure the data since it's going Wi-Fi? Do you guys use any kind of encryption, or is it WPA2 or?
Right. So 2 levels of encryption. Yeah, there is a WPA2 PSK on the Wi-Fi side, but also all of this is encrypted. This data is encrypted. AES 256 refers to the cloud, and once it gets to the cloud, HTTPS TLS 1.2, right, to get and there's multi-factor authentication. Yeah.
Thank you. One more question, very quick. The sensors are, I guess, they are accelerometers. And the question is, do you have experience with low frequency, low speed analysis by accelerometers? Because, okay, the pump are running maybe at 1700 RPM or something like that. So, but if you have very low speed shafts, can you do something also or not?
Great question. Yeah. So usually this is on the bearing housing, and this is recommended for speeds 300 RPM and above. Below 300 RPM, we don't think you should be doing procs and displacement measurement and things like that. Not velocity measurement, acceleration pickups. Because then because you're integrating acceleration essentially to get velocity, and then you have to integrate again. There will be errors there, right? So we don't recommend for very slow speed machines, right? 300 RPM we have monitored. Actually, MEMS sensors are really good for low RPM machines. So they work well in the low RPM compared to traditional piezo sensors. Right. So that would be our approach. We would try and get a prox probe onto the transmitter and get the data out. That's kind of our approach right now. Displacement, measure displacement. Yeah.
Hi, I have a very quick question. So could you refresh my memory about the mechanism you used to send the notifications? Did you use any Pi notifications to send out the email that contains the vibration data?
Right now, we're using notifications directly from Petasense. We're in the process we're still on Pi 2012, so we're a little bit behind. But yes, very shortly we're going to be switching to AF and leveraging all those great notifications that are in with AF.
And event frame some of these things.
Yeah, and event frames. And
Yeah.
so we're also looking at integrating, like an electronic logbook, but that's with somebody else. So we'll use event frames to populate, a trend in data into our shift turnover reports with a trend if there's an event.
Okay.
Right, thanks.
Do you guys ever experience on your site problems with like harmonic frequency vibrations that cause trips, whatever your interlocks are, to a certain piece of equipment?
No, we haven't really experienced anything like that.
I mean, is Petasense capable of discerning whether it's just a harmonic frequency issue?
Sorry,
And
can you repeat your question? I would like to understand more.
yeah, so I was wondering if they ever experienced problems with harmonic frequency, like vibrations at whatever speed for any reason, that cause your piece of equipment to trip based on whatever your interlock is. And if Petasense has the capability to kind of filter out, like, okay, we recognize this isn't a failure problem. This is just a vibration associated with a certain frequency.
Right. So you see the way at a high level it works. By the way, we don't do
The Petasense isn't doing any controls
protection, yeah.
or protection.
Right.
So on our gas turbines and on our steam turbine, we have our traditional Bentley racks, and based off of the voting and stuff in that's what's going to initiate a trip. So Petasense doesn't do any controls. We're not using it for any controls. It has no connection to our control system.
Okay, so you don't use any feed forward information to your...
no.
No, we use it for decision making, but it's not in our operations as far as an automatic trip or something.
On the frequency, on the spectrum, we can identify what's a defect, what's not. We for example, we input bearing numbers, we input the running speed. So we input things like number of vanes, number of vanes in an impeller. So we can understand some of the defect frequencies. We can label them on the graph, right? That's where we do, and then we can set alarm levels for each of them, and we send them an alert. After that, yeah, it's not shutting anything down.
Thanks.
Yeah.
Yeah, at my previous company, the plants would ask me, well, what all data do you want to get into Pi? And my answer was always all of it. And then besides all of it, I want everything else. I want the weather there. I want forecasting. And then besides that, we would do a CBM gap analysis, right? We'd find this equipment that we have, we really didn't have information on to determine its health. And this is a fantastic way to add instrumentation to make it more robust. If you were here for AGL's talk, you know that they had a $50 to $70 million catch on a few thermocouples. So how valuable is a few sensors? They're extremely valuable, especially if you're monitoring them and you're looking at them, right? So guys, I really want to thank y'all very much. A great presentation.